Bismillahirrahmanirrahim. Assalamu alaikum dear students. We are now starting the second lecture for week number 7 of our course of communication systems. We are in the previous lecture we are having discussion related to frequency modulation and the practical implementation of this frequency modulation scheme. We also had some discussion on some simple problems related to the frequency modulation. Continuing the discussion of our first lecture of this week, we'll be having some more problems in this lecture. So let us start by taking another problem. So we have a simple problem here, a frequency modulated signal which is modulated by a 3 kilohertz sine wave. So we are giving a modulating signal. You should notice that this is not the carrier, this is the modulating signal or audio signal whose frequency is given as 3 kilohertz. So the audio signal has a frequency of 3 kilohertz which is given in this problem, and we are given that this reaches the maximum frequency of 100.02 megahertz and the minimum frequency of 99.98 megahertz. So we know that because for frequency modulation there is change in the frequency. So what is the maximum frequency attained by the modulated wave and the minimum frequency attained by modulated wave is given. So maximum value of the frequency and minimum value of the frequency are known, and from this information we want to find these things. First we want to calculate the carrier swing, second is the carrier frequency, third is the frequency deviation for the signal, and the modulation index of the signal. So we want to find these 4 parameters here. So let us now start with the carrier swing. We know that the carrier swing is actually represents the range of frequencies which represent the variations obtained by the frequency modulated signal. So the carrier swing should be represented as the difference between the maximum frequency obtained and the minimum frequency attained by the modulated signal. So CS is actually F max minus F minimum, which is given by these values, 100.02 megahertz and 99.98 megahertz. So if we find out the difference, you would see that the difference is 0.04 megahertz. In other words, we can say that the carrier swing in this case is 40 kilohertz. Second thing that is required in this problem is the carrier frequency. What is the carrier frequency, which is also named as resting frequency? From the beginning we are assuming that there is a symmetrical deviation at the higher lower side of the carrier frequency. So maximum frequency delta F represents the maximum positive change obtained through frequency modulation, and minus delta F represents the minimum change that is obtained through the through the frequency modulation. So the maximum, so since we are taking the symmetrical change in both sides of the carrier frequency, therefore we can conveniently say that the carrier frequency should be halfway between the maximum attained frequency and the minimum attained frequency. So the carrier frequency should be exactly between the maximum and minimum frequency, or in other words, the carrier frequency should be a mathematical mean or average of the maximum and minimum frequency. Therefore we can calculate the carrier frequency by summing the two frequencies and dividing by 2. So if we sum them together and divide by 2, we would see that the carrier frequency comes out to be 100 megahertz. third thing that is required in the problem is frequency deviation, delta f. So what is delta f? We can calculate delta f by a number of ways here, as we know that the delta f, the frequency deviation, is half of the carrier swing. So if we divide carrier swing by 2, you would see that the delta f comes out to be 20 kilohertz. Alternatively, you can also calculate delta f from the relationship of maximum frequency. We know that the highest frequency obtained, fh, is actually carrier frequency plus delta f. So if you use this relationship, you can also calculate the frequency deviation from this relationship, or a similar relationship that we have for the lower end of the frequency. So delta f comes out to be 20 kilohertz for this case. The last thing that we need to calculate is the modulation index. Modulation index has the simple formula here, which is the ratio of the frequency deviation and the modulating frequency. So if you divide delta f by fa, which is 20 divided by 3, so we get modulation index to be equal to 6.66. Okay, let us take another simple problem here. So for a specific FM transmission which is used in a specific region, we are given that the frequency deviation is set to 20 kilohertz. So the frequency deviation is 20 kilohertz used in the FM transmission, and we want to find percentage modulation. So percent modulation is needed for two cases. First is actually the signal is broadcast as FM radio in the FM band of 188 to 108 megahertz. So whatever frequency they are allocated, so they are transmitting a radio broadcast. Second, we want to calculate the percentage modulation if we are using this FM as an audio portion of the television broadcast. Audio portion of the television broadcast is of course also uses FM modulation, as we discussed before. So we want to find a percentage modulation for these two cases, for FM broadcast and percent modulation. We know that and TV audio broadcast. We know that the percentage modulation for FM wave is given by this formula, where M is representing the percentage modulation. Delta F actual is actually the represents the actual implementation of frequency deviation, which for our case is 20 kilohertz. You can see that the transmission is set to have the frequency deviation of 20 kilohertz only, whereas delta F max is representing of maximum allowed frequency deviation. And we know that for the audio portion, for the FM broadcast band, we know that the FCC has set the upper limit of frequency deviation to be 75 kilohertz. So the maximum allowed frequency deviation is 75 kilohertz, whereas actually used frequency deviation is 20 kilohertz only. So if we divide these two together, 20 divided by 75, we would see that the percentage modulation comes out to be 26.67% for the case where we are using FM broadcast band for transmission. Similarly, if we use the FM broadcast for TV transmission, audio portion of TV transmission, in that case we know that the FCC has set the upper limit of 25 kilohertz for frequency deviation. So maximum allowed frequency deviation is 25 kilohertz for the case of TV broadcast, and whereas the actual broadcast actual deviation which is used in the system is 20 kilohertz as given in the problem. So if we divide these two, in that case we will get that this modulation index to be equal to 20 divided by 25, which comes out to be 80%. So for television broadcast or audio version of television broadcast, this modulation index comes out to be 80% for this particular case. Let us take another simple problem. Determine the bandwidth of narrowband FM signal which is generated by 4 kilohertz audio signal. You should see that there are two key terms here. One, if we have 4 kilohertz audio signal, so audio frequency is given 4 kilohertz. Second thing which is given is the narrowband FM signal. Narrowband FM signal is the signal where you have restricted the modulation index to a certain limit. Modulating carrier frequency, so the carrier frequency is given as 125 kilohertz, of course 125 megahertz, sorry. Although for this particular problem the modulating frequency is not critically important, because we are interested in calculating the bandwidth of narrowband FM. Theoretically speaking, if you recall our discussion related to the bandwidth, we know that in order to calculate the bandwidth of modulated signal, FM modulated signal, we have to look at the number of significant sidebands. We had discussion on the number of significant sidebands in our last week's discussion. You can refer to that. And you should realize that the number of significant sidebands affect the bandwidth of the FM signal. However, we have also discussed that there is a special case of FM which is named as narrowband FM, and in that case the bandwidth of FM signal is taken equal to the bandwidth of the AM signal, that is double of the message signal. For narrowband FM case, the bandwidth should be double of whatever message signal or audio signal you are using, so that will give the bandwidth. So for this particular case, the bandwidth should be 2 into FA, so you can simply multiply 2 by this 4 kilohertz in order to get the bandwidth of 8 kilohertz. So this is this is the bandwidth for narrowband FM case here. At this stage, I want to mention one more practical practical consideration here. For narrowband case, as I mentioned earlier in the last week's discussion, that we consider only one significant sideband, that is one sideband at the upper side and one sideband at the lower side. So practically all those FM cases where the modulation index is less than pi by 2, the value of pi by 2 comes out to be around 1.57. so if the modulation index has the value smaller than pi by 2, so practically all those transmissions, they are considered as narrowband FM. So this is a common implementation or design consideration. So if we want to have a narrowband FM, we generally try to keep modulation index below this limit of pi by 2. This brings us to another very important topic, which is the frequency multiplier. Frequency multiplier is a very important component in many FM systems. Actually, what happens, generally the FM signals, they are generated by low power circuitries. So generally these low power circuitries, they provide frequency deviation which is generally a small value. So the frequency deviation which is generated by FM circuits or low level FM circuits, they are not large enough. The transmission requires us to have significantly large amount of the frequency deviation. For example, if you consider the audio transmission for FM broadcast, you should realize that the FCC has set the limit of frequency deviation to be equal to 75 kilohertz. So 75 kilohertz is a large value, so we do not typically the circuits do not typically generate such large amount of frequency deviation at the first stage. So what we need to do, we need to increase that frequency deviation. We want to increase the frequency deviation, and in order to do that, we should pass it through a special circuit which is called frequency multiplier. What is the frequency multiplier? Frequency multiplier is a circuit which generates typically it generates harmonics of the system. Harmonics means if it's a second harmonic, that means it will generate the double of the frequency which is applied at the input side. Similarly, the third harmonic represents the signal which has the frequency which is 3 times the what is applied at the input side. Similarly, the fourth harmonic would be representing the circuit which system which generates the fourth multiple of the frequency which is applied at the input side. So frequency multipliers, they generally generate the harmonics, and we get the desired harmonic at the output by a proper filtering. So this frequency multipliers, they actually multiply the overall frequency by a certain constant number, say for example s. So I have used a constant number s. So whatever s is there, the overall frequency would be multiplied by that particular number, and you can see that at the end this carrier frequency would be increased by this factor of s, whereas this delta f is also increased by a factor of s. You can see that whatever frequency deviation you had at the input side, the output side would have a frequency deviation which is s times higher than the previous the input side frequency deviation. You should also notice that the carrier frequency is also increasing, so carrier frequency also becomes s times the old carrier frequency. So these frequency multipliers, they are important components in order to increase the frequency deviation to the desired level by using those frequency multipliers. At this stage, although theoretically speaking we can have frequency multiplier of any order, but practically we only have frequency multiplier which are creating double or 3 times frequency. So we only have frequency doubler or frequency tripler. So practically if we want to create a frequency multiplication factor of, say for example 12, so in that case you have to pass the signal by 2 doublers and 1 tripler. So 2 into 2 into 3, so you have to increase the frequency at 3 stages. It will pass through 3 frequency multipliers in order to get an overall multiplication factor of 12. So practically this frequency multipliers they are implemented in form of doublers or triplers only, and in order to get a higher multiplication factor you need to pass the signal from a number of frequency multipliers so that you get the desired amount of the multiplication factor. In addition to the frequency multiplying, there is another important term which is heterodyning, which we have also previously used in the discussion of AM modulation. Heterodyning, the term heterodyning refers to the frequency mixing where you either add or subtract the frequency. So heterodyning is actually create the multiplication of 2 frequencies, and eventually when you expand those frequencies you get the sum of frequencies and difference of frequencies. And by appropriate filtering, sometimes you need to filter if you need to have you want to increase the frequency. In that case you have to filter out the positive frequency component, and if you want to decrease the frequency, you have to filter out the negative frequency component. You have to extract that negative frequency component. So by using the appropriate filtering, you can extract any of these components. So this heterodyning refers to the addition and subtraction of the filtering. So after multiplier, sometimes we need to add or subtract the frequencies by using a local oscillator. You should note that this heterodyning does not affect the frequency deviation. It does not affect the frequency deviation. Rather, it only adds or subtract in the carrier frequency. So it will only change the frequency by a certain number, carrier frequency number, and it will not change the frequency deviation. So these two are important aspects related to the implementation of our FM systems. We need to incorporate frequency multipliers as well as the heterodyning, so that you can get your signal to the desired frequency deviation value and the carrier frequency value. In order to understand the impact of this heterodyning and the frequency multiplication, let us take a simple problem here. So we have this problem. So we are given a block diagram which is illustrated in this figure, and we want to find what is the total carrier frequency and the frequency deviation at this output at this stage number 3 here. And we in order to doing so, we will be calculating the frequency deviation and the carrier frequency at all these intermediate stages. You can see that the input signal, although we are not given the input signal, but we know the important parameters related to input signal. It is given that the carrier frequency input to this circuit is 7.5 megahertz, whereas the frequency deviation is given as 6 kilohertz. This is passed through a multiplier having a multiplication factor of 3, and then it is also passed through another multiplier which having a multiplication factor of 4, and then it is passed through a heterodyner or frequency mixer which is mixing a frequency which is coming from an oscillator of 6 megahertz. So local oscillator has a frequency of 6 megahertz. So generally, since we are talking about the transmitter, so transmitters tend to increase the carrier frequency. So we will consider that this oscillator is actually adding this frequency of 6 megahertz here. So let us now start this problem. So the carrier frequency is given. So the carrier frequency at the 0th stage or initial state is given as 7.5 megahertz, and delta F is given as 6 kilohertz, and we want to find this carrier frequency and delta F at all other stages, stage number 1, 2 and 3. So I have differentiated them by using an appropriate subscript. So if you look at this stage number 1 here, you would see that this carrier frequency and delta this frequency deviation, they are passing through a multiplier having a multiplication factor of 3. So that means at the stage number 1 you would see a carrier frequency which will be 3 times higher than the carrier frequency at the input side, whereas the frequency deviation would also get multiplied by this factor of 3 as compared to what you have at the input side. So the carrier frequency FC1 at the stage number 1 will be 3 times of the actual carrier frequency, 7.5 megahertz. So at stage number 1 you would see a carrier frequency to be equal to 22.5 megahertz. Similarly, the frequency deviation would also get multiplied by the multiplication factor of 3. So this multiplication factor of 3 represents that the carrier frequency the frequency deviation at the stage number 1 would come out to be 18 kilohertz, because we have 6 kilohertz frequency deviation at the input side. So now we know the frequency deviation and the and the carrier frequency at this stage number 1, we can using these values we can calculate the frequency deviation and carrier frequencies at the stage number 2. You can see that from 1 to 2 we have a frequency multiplier having a multiplication factor of 4. That means from stage number 1 to stage number 2 you would see that the carrier frequency would also be multiplied by a factor of 4, and the frequency deviation would also be multiplied by a factor of 4. So if you want to find the carrier frequency at the stage 2, it will be 4 times the carrier frequency which you had at the stage number 1 here. So this comes out to be 90 megahertz, multiplying this 4 by 22.5. Similarly, the frequency deviation at the stage number 2 will be actually 4 times the frequency deviation at the stage number 1, which is 4 into 18, which comes out to be 72 kilohertz. Now we know the carrier frequency and the frequency deviation at the stage 2. We can now calculate the both the parameter at stage number 3. You can see that this is a heterodyner, not a multiplier. So as I mentioned earlier, that heterodyner only shifts the frequency, add or subtract the carrier frequency, so it will not create any change in the frequency deviation. So whatever frequency deviation you have at the stage number 2, the same frequency deviation would appear at stage number 3. So at stage number 3 the frequency deviation would be same as what you have at stage number 2. So the frequency deviation would be 72 kilohertz only, as we have noticed for the stage number 3. However, because of this heterodyning, the carrier frequency would get changed, and the change would be equal to the frequency of this local oscillator, which is 6 megahertz. And because we are working on transmitter, so we will be assuming that it is creating increasing the frequency, so it's up converting the frequency. So whatever frequency you have at stage number 2, carrier frequency you have at stage number 2, it would be having a higher frequency by a number 6 megahertz. So 6 megahertz would get added to the carrier frequency. So you can see that FC3 would be whatever carrier frequency you have at stage number 2, this will be added with this local oscillator frequency. If you add them together, 90 megahertz plus 6 megahertz, it comes out to be 96 megahertz. So the overall output would have a carrier frequency of 96 megahertz with a frequency deviation of 72 kilohertz. You can see that in this way we can increase the carrier frequency as well as the frequency deviation by using a combination of multipliers and the heterodyners. So from this we understand that we can shift the frequencies and frequency deviation to the desired value. So we would stop the discussion of this lecture here. The last topic which will be covered in lecture number 3 for this week is related to the transmitters and receiver circuitries that we use for FM and PM. So we'll stop here. Thank you all. Allah Hafiz.